In this lecture, I am going to discuss what is meant by whirling speed of shaft, what is the need of calculating the whirling speed of shaft, and the calculation of whirling speed of shaft for any cantilever or simply supported shafts. So before going to the whirling speed of shaft, we will discuss the natural frequency of transverse vibration. Okay. So transverse vibration means the system will vibrate perpendicular to its axis. Okay. So the system will vibrate like this. Fine. So mostly the beams are subjected to transverse vibration. Okay. So the equation for calculating the natural frequency for a transverse vibration system is Fn is equal to 1 by 2 pi root of g by del. So here g is the gravitational force and del is the deflection because of the load acting. Okay. So for cantilever beam and simply supported beam, we are going to see the equations for deflection. So first for cantilever beam, subjected to a point load at the free end. So cantilever beam means the beam is fixed at one end and in the other end it is subjected to a point load W. Okay. So here the maximum deflection will be there at the free end. So the equation for calculating the deflection is del is equal to WL cube divided by 3EI. So W is the point load, L is the length of the shaft, E is the Young's modulus of the material and I is the moment of inertia. Then for cantilever beam carrying uniformly distributed load throughout its length is del is equal to WL cube divided by 8EI. So here W will be in Newton per meter since it is a uniformly distributed load. Then for simply supported beam with point load at the center, the maximum deflection will be there at the center. Okay, so the deflection will be like this. So here you will have the maximum deflection and the equation for maximum deflection is del is equal to WL cube divided by 48 EI. Then for cantilever beam, simply supported beam with point load acting with some eccentricity, the equation is del is equal to WA square B square divided by 3EIL. Then in the case of simply supported beam with uniformly distributed load, the equation is del is equal to 5 by 384 WL power 4 divided by EI. So in shafts, the shafts having flexible bearings are considered as simply supported beams and the shafts supported in long bearings or rigid bearings are considered as rigid beams. Okay. Then the Dunkerley method. Okay. So when a shaft is subjected to more than one load, then we can use the Dunkerley method to find the natural frequency. So the equation is Fn is equal to 1 by 2 pi root of G divided by del 1, del 2, del 3. In case of uniformly distributed load, then it is del S divided by 1.27. Okay, so I think in the dynamics you might have studied the derivations for this, so I am not going to solve the derivations. So for uniformly distributed load, we have to divide the deflection by 1.27. So here del 1 is the load acting, deflection because of the load W1 and del 2 is the deflection because of W2 and del 3 is the deflection because of W3 and this del S is because of the weight of the shaft. Okay, so the weight of the shaft is actually considered as uniformly distributed load. So most of the cases they will specify the mass density rho. Okay, so if the mass density is given, then you can calculate the weight by weight is equal to mass density into volume. Okay, so by multiplying the volume with the mass density, if the density is in if mass density means it will be in kg per meter cube. So if you multiply meter cube with it, that is the volume, then you will get in kilogram. Okay, so actually we have to substitute the value in meter, so you can convert that kilogram into Newton. Okay, so that is how we have to solve the systems having more number of loads. So now we'll move into the whirling speed of shaft. Okay, so whirling speed of shaft means the natural frequency at which the transverse vibration occurs. Okay, so when the externally applied frequency of the system matches with the transverse vibration of the system, then the system will vibrate with high amplitude. Okay, so the corresponding speed at which the resonance occurs is called as critical speed or whirling speed. Okay, so at whirling speed the deflection will be very high. Okay, so you might have done the experiment in your dynamics laboratory. When the shaft is running with its critical speed, then the deflection will be very high. Okay, so that is the dangerous part of critical speed. So every system has many degrees of freedom. So based on the degrees of freedom, the system may have a n number of critical speed or whirling speed, but we are going to focus only on the lowest critical speed. Okay, so the purpose of calculating the critical speed is, once if you calculate the critical speed of the system, then you should not run the machine at that particular speed. For example, if the critical speed of the system is 500 rpm, then you have to give some 10% deviation. So 10 rpm deviation. So you can run up to 490 rpm, or otherwise you can run from 510 rpm. Okay, so you should not run in between 490 to 510 rpm. That is very dangerous for the system. So if you continuously run the system in resonance speed, that is at critical speed, then your system will break. Okay, fine. So now we will calculate, we will see how to calculate the critical speed of the system, so that while using any shaft for any applications, we can adjust the speed of the external forced vibration to neglect the resonance. So first I'll start with the simple problem that is having only the point loads. A shaft 50 mm diameter and 3 meter long is simply supported at its ends and carries 3 loads of 1000 Newton, 1500 Newton and 750 Newton at 1 meter, 2 meter and 2.5 meter from the left support. Okay, so here the shaft is a simply supported one. Okay, so the beam is a simply supported beam and it is supported at its ends. Then it carries 3 loads, 1000 meter at a distance of 1 meter, 1500 Newton at 2 meter, then 750 Newton at 2.5 meter. The Young's modulus of the shaft material is given, that is E is equal to 200 gigapascal. Gigapascal means it is 10 power 9 Newton per mm square. Sorry, it is Newton per meter square, 10 power 9 Newton per meter square. Find the critical speed of the shaft. So we have to calculate the critical speed of the shaft. So first we have to calculate the natural frequency of transverse vibration. Then after that we can convert that natural frequency into critical speed. Okay, fine. So the equation for calculating the natural deflection for eccentric loading is WA square B square divided by 3EIL. So I am going to consider this 1000 Newton as W1. So first I am going to calculate del 1. So that is W1 A square B square divided by 3EIL. Fine. So W1 is 1000. A for this W1 is 1 and B is the distance at the opposite side, that is 3 minus 1 meter is 2 meters. So 2 square divided by 3. E is given in the problem, that is 200 into 10 power 9 Newton per meter square. So here I have substituted everything in meter. Then I, the moment of inertia. Okay, so we know that the equation for moment of inertia for a circular cross section, that is solid circular cross section, it is pi by 64 d power 4. So in the case of hollow circular section, it is pi by 64 outer diameter power 4 minus inner diameter power 4. So here it is a solid section. So I am going to substitute the value of diameter. So better you can substitute the value in meter. Okay, so I have substituted in mm and I have converted into meter. So if you want better, you can substitute as meters value. So you will get the value as 30.7 into 10 power minus 8 meter power 4. You can substitute that. So if you solve this equation, finally you will get the del 1 value as 7.24 into 10 power minus 3 meter. So this is the deflection because of the W1. Then the next load is W2, that is 1500 Newton. Okay, so here the load is replaced with 1500 and the A for 1500 is 2 meter. So the remaining length is B 1 meter. So the remaining data are same. You will get del 2 is equal to 10.86 into 10 power minus 3 meter. So similarly for del 3, I mean W3, it is 750 Newton. So 750 Newton. So here the A is actually 2.5. So there is a mistake here. The A is 2.5 square and the B is 1 square. Sorry, 0.5 square. Okay. Yeah. Fine. So if you solve this, you will get 2.12 into 10 power minus 3 meter. So this is the deflection because of load 3. So now by using the Dunkerley's equation, there is no uniformly distributed load is here. So all the three loads are point load. So the equation is 1 by 2 pi root of G by del 1 plus del 2 plus del 3. So you can substitute the value of del 1, del 2, del 3 and G so that you can calculate the natural frequency of transverse vibration, that is 3.5 hertz. So actually hertz means it is revolutions per second. So to convert this revolutions per second into a speed, that is critical speed, I have multiplied 6. So 3.5 hertz into 6, that is equal to 210 rpm. So this is the critical speed of this shaft. Okay, so you should not run this shaft at this 210 rpm. Fine. The second problem, calculate the whirling speed of a shaft 20 mm diameter and 0.6 meter long, carrying a mass of 1 kg at its midpoint. Okay. Then the density of the material is 40 megagram per meter cube. So here the density of the shaft material is given. So previously in the problem the density is not given. So we have neglected the weight of the shaft. But here the density is given, so we have to calculate the weight of the shaft and we have to consider it as a uniformly distributed load. Okay, and Young's modulus is 200 gigapascal. Assume the shaft to be freely supported. Okay, so this is the given drawing. The diameter is 20 mm, that is 0.02 meter. E is 200 into 10 power 9 Newton per mm square. Rho is 40 megagram per meter cube. I have converted into kilogram per meter cube by multiplying 10 power 3. Okay. So first we will calculate the weight of the shaft. As I told earlier, the weight can be calculated by volume into density into gravity. Okay. So area into length will give you the volume. So area is pi by 4 d square, length is L, density is rho and the gravity is G. So you can substitute everything in this equation so that you can calculate the weight of the shaft, that is 73.97 Newton per meter. Okay, so now he has calculated the weight of the shaft. Also the shaft is subjected to a point load at the center. So actually the weight is given in 1 kg. I have converted it into Newton, that is 9.81 Newton. So for simply supported beam subjected to point load at the center, the equation is WL cube divided by 48 EI. Okay, so I have substituted the value of W, L, E is given in the problem, I we have to calculate. So the equation, so here it is a solid shaft, so I is equal to pi by 64 d power 4, D is 0.024, the I value is 7.85 into 10 power 9, 10 power minus 9 meter power 4. So you can substitute that. So after solving this, you will get del 1 is equal to 2.8 into 10 power minus 5 meter. Then for simply supported beam carrying a uniformly distributed load, that is the weight of the shaft, the equation is 5 by 384 WL power 4 divided by EI. So here the W is the uniformly distributed load, that is 73.97. You can substitute that. Then length, the remaining data are same. So you can calculate the deflection because of the weight of the shaft. So 7.95 into 10 power minus 5 meter. Okay. So now we have calculated the individual deflection. Use the Dunkerley's equation, that is 1 by 2 pi root of G by del 1 plus for uniformly distributed load just divide 1.27. So substitute the values. Finally you will get the natural frequency of transverse vibration is equal to 52.37 Hertz. Fine. So this is the natural frequency. Remember that you have to convert the hertz into RPM. So multiply 60 with it. So the critical speed is equal to 3142 RPM. So this is the solution. Okay, so now I have discussed two problems on simply supported beam with only point load and a uniformly distributed load. Okay, so I have two tutorials. The first one is a steel bar 25 mm wide and 35 mm deep. So here it is not a simply circular cross section. So here it's a rectangular cross section, and we know that the moment of inertia for rectangular cross section is BH cube divided by 12. So it's not pi by 64 d power 4, it is BH cube divided by 12. It is freely supported at 2 points 1 meter apart. So the length of the shaft is 1 meter and carries a mass of 200 kg in the middle of the bar. Neglecting the mass of the bar, find the critical speed. So the bar is subjected to only 200 kg at the center. Convert this into Newton. Okay, so here another part of the problem is, if an additional mass of 200 kg is distributed uniformly over the length, what will be the critical speed? Okay, so case 1 is by considering the central point load alone. Case 2 is an additional 200 kg is distributed uniformly over the length of the shaft. Okay, so by adding another uniformly distributed load, what will be the change in critical speed? So the E is given. Okay, so two cases. For case 1, the answer is 1068 rpm, and for case 2 it is 876 rpm. The second tutorial problem is a shaft of diameter 10 mm carries at its center of a mass of 12 kg. Okay, so it carries 12 kg at its center. It is supported by two short bearings. The meaning for short bearings is we can consider the shaft as a simply supported one. Okay, remember that for short bearings it is simply supported. For long or rigid bearings, then it is fixed beam. Okay, so be clear about it. The center distance of which is 400 mm, the length is 400 mm. Find the whirling speed. First one, neglecting the mass of the shaft, and second one, taking the mass of the shaft into account. The density of the shaft material is 7500 kg per meter cube. So here also two cases. The first one is only by considering the central point load, so convert it into Newton, and the case 2 is by considering the weight of the shaft. So it is del 1 and del S, a point load and a uniformly distributed load. So calculate the critical speed for both the cases. So for case 1 it is 748 rpm, and for case 2 it is 744 rpm. Okay, so you just practice the two tutorial problems so that you will get a clear understanding about the calculation of critical speed.